Well, I think we're there. Welcome back, everyone. We're at the very end of week 13, and other exciting news so far for the announcements is this is probably going to be our very last section of the semester. So we're nearly complete. Congratulations for almost being there. With what we have going on today on the announcements, Quiz 7 is due today. And even if you don't have it completely finalized today, continue to work on it, get it solved as nicely as possible. I'll accept it late and I'll be grading these over the weekend. It's an important quiz because it's targeting section 4.4 specifically. And we gave out a pretty big hint on that 4.4 section. The problem that's going to be asked on the exam is going to be pretty similar to that quiz number 7. Next, quiz number 8. This one is based off section 4.6 on antiderivatives. So if you decide to come back to quiz number 8 after the exam, that might make a lot of sense because this information isn't on the third exam. It would be on the final exam. So that's where we're at so far. Ordinarily, we jump back into section 5.3 and continue working. But like we mentioned, we'll allow today's Tuesday class to be a kind of impromptu review day. The exam is going to be off these sections here, and I'll turn it over to the class at this point. Any questions that folks would like to discuss to help prepare?
Local max, min, stuff like that.
4.1, absolutely. Let me add a new file here before I forget, just so we can save these results. We'll call this Exam3 review. And just like the other exam reviews, I'll post whatever problems we work on right here. Just titled the Exam3, let's be a little bit more specific, in class review. Okay, so taking a look into the graphing section, 4.1. And we can get a problem from here, but this one's right out of the textbook. Version 2 are the notes we solved. And version 3 should have some new problems, so that might be a good place to start. Let's see, for version 3, we have this graph. Is this kind of on the lines that you're thinking about? That's a good choice. I think these problems are pretty tricky in all honesty. So let's be careful with this one. This is a good one to start us off. So this one is section 4.1. We did do one like this in class, so that's already a pretty big hint on its own right. That makes it qualify as a pretty good exam question. The goal on this one, classify all extreme values, but specifically, we're looking for the absolute and local maximum and minimum values, every single one as we find them, of the function. And this is a pretty tricky problem, even on an exam setting. So let's be really careful with this one. Very methodical. First value we have over here at 0. Let's take a look. At 0, we're right at a boundary point. So this cannot be a local minimum. Also, it's not an absolute minimum because values over here are just a little bit lower. So let's say what we said about that one. But first, let me complete the scale on here so we're not counting off over and over again as we run through this problem. Okay, so our scale is completed. And maybe the first comment to make. This is the boundary of the domain. So we can say, we call this whole function y equals f of x. F at 0 is not a local min for this problem. So when we start at 0, we have nothing here for a local minimum. So we just move off to the next point. Something interesting happens right around here. So right when x is 1, that is something we have going on. Let's color code these up a little bit just to see this better. So at f of 1, we get a value out at height 3. This one is either a local maximum or a local minimum. Anyone see which version that one should be?
Say local max, but we can, it's not there, it's nothing. It would be nothing if the point isn't.
Well, that's a good point. Yeah, the point right here, which would have given a local max, is not defined at that spot, but it is defined. It takes on this value. So that makes this question just like supremely tricky already right at that value. So it's either a maximum or a minimum. It's really one or the other. And let's see which one it could be. I agree with you because it seems to go upwards like that, but then there's no maximum value there, and then it climbs back down. So this one is not a maximum, it turns out. It's a minimum, and it's really hard to see why. It's a specifically local minimum. Maybe the best strategy to really see this, though, is on an exam setting, use your hands to kind of block off the left side and the right side of the graph. Or if you're studying, you might have note cards. So let's pull up some note cards. So we can put in some blinders that go like this. This is hard to move. Hang on. Putting a little bit of a blinder going over like that. Another blinder going over like this. And now when we're only focusing on this part of the curve, the situation kind of clarifies a little bit better. Right in this local region, this is what we mean by a local minimum, that value, which is at height 3, is lower than every other single function value. All of these are higher on the left. All of these are higher on the right. That makes this one the minimum, and locally, it's the smallest value on that whole range, right around 1. So we have f at 1 equals 3 is a local minimum. Let's pause right there, though. Does that make sense to folks so far on how we spotted that as a minimum?
When you put it down in the test, we'll say at that something, and then we have to say the y point.
I think if you did ignore the y point, I wouldn't be too worried about that. But I think it is good to include for sure. If you just said f of 1 minimum, or if you said x equals 1 minimum, I would have accepted both answers in that case. All right, let's clear this off. Oh, there you go. Different way to do that. Now, revealing the whole graph, we can say f at 1 equals 3. This one is a local minimum. I don't know why I color code that halfway, but there we go. Local minimum on that one. So first point was extremely tricky. No local mins or maxes at the boundary. The domain starts right at 0, so that makes it a boundary value. Here, that looks like a local maximum, but if you just delete that point or redefine it below, it's really a local minimum. And now we move on down to this stage. Now we're at 2, and this is a little bit more standard, right? What would you all say for the value at 2? Is that a max or a min? Yeah, if it's coming down and then peaking out, or then bottoming out and coming back up, we're looking at a local min again. So let's say here, f at 2 equals 2 is a local minimum value for that one as well. So 2 local mins. Now we just move off to the next interesting spot. I'm forgetting don't want to delete the scale there. Nothing interesting happens at 3. That's because it's just increasing and increasing. If you're increasing all the way around 3, there's no local anything or absolute anything. But then this is the next most interesting spot. Right at 4, where the red dot is currently, that's the highest point on the entire curve. So we would probably call this one f at 4. Output to that one is 5. This one is an absolute maximum. So we have an absolute max on that one. Then coming down, right at 5, the curve just looks funny. But sure enough, right in this region, I'm not sure, I thought I had a pen tool going there. Right in this region, that point right there is lower than anything slightly to the left, anything slightly to the right. So right at 5 is another local minimum. Let's write out for this one. F at 5 equals 3 is a local min. If it feels kind of funny, I agree with you. That point right there is just different than all the other points. Sorry, try to erase that. It just doesn't want to die. It really is a different point. There we go. Jeez. Something weird has happened on the multiple layers of this digital ink. Sorry, I think I deleted a result. F at 5 equals local minimum. Microsoft Word really doesn't like how I put this file together, I guess. So we have a local minimum there. And now looks like another really troubling point right at 6. First, let's evaluate it. F at 6 takes on height 4. And we need to decide right at this value, is that a local minimum or a local maximum we're looking at? It turns out this one is absolutely one or the other. It's just really hard to see. And notice what makes these hard is the discontinuities. This one's a removable discontinuity. If you just redefine something in a weird way, it's really hard to see the max or min. This one's even worse. It's a full-on jump discontinuity, and it's tricking us into not quite seeing the max or min on it. But then use the strategy of just cover up the region around 6 on an exam with your hands, scratch paper, anything like that, and it really reveals a little bit more. Right around 6, that value 4 as an output is the highest value in this region. That makes it a local maximum. But again, this is a problem where you'd probably want to answer it kind of carefully on an exam setting. Spend like 5 minutes on it, really a minute per part. Time yourself well, put your results down, and then ignore the problem for the rest of the exam. When you're about done with the exam, come back to this one and just look over your work. See if anything jumps at you that would really strongly change your mind. And if it does, make some changes. But if you feel like it's about right, usually your first inclination on these are the right gut choice to go with. But it's a good problem to look into several times because of its trickiness. So f at 6 equals 4 is a local max. So another maximum, only local on that one. And then finally, we move over to 7. Now, this one's really, really tricky. It's the lowest point. Well, not exactly, it's undefined. This one was defined, but it's not the lowest point on the graph. These values go a little bit lower, so we couldn't call that an absolute minimum. And if it was filled in just like this, that makes it an absolute minimum right at that spot. This is a tricky enough problem that let's see this as 2 versions. Here's version 2, the nicer version down below. In version 2, we're leaving that point solidified. And if that's the case, we would say f at 7 takes on height 1 is the absolute minimum. Microsoft is really slow today. There it goes. So we would have an absolute minimum if that solid dot was filled in. But we've seen this also in the notes in section 4.1. Take out that solid dot. There we go, back to the original graph. And it can't be a local minimum here because we're at the boundary. And it can't be an absolute minimum either because f of 7 is undefined. Something undefined like that can never give you a max nor min of any kind whatsoever. So the last point was also a tricky point as well. Really, the dangerous points on this problem are right at here, x is 0, right at here, because of the discontinuity, x is 1, then routine values until we get to here. The curve just looks weird because of the sharp corner, but that's allowed. And then another problem right over here because of the jump discontinuity, and another trick right down here because we left f of 7 undefined. So a very concerning problem, but really as a review problem, that's the point, just to show you all the weird things that can happen. Exam questions aren't necessarily going to be just loaded with trick questions or tricky situations like this. But to just finalize the notes on this one, if you find it undefined, not like f at 1, f at 1 is defined, it comes out as 3. But this one has no solid dot defined anywhere on the region they gave us. So for this one, there is no extreme values whatsoever. So there can't be a maximum or minimum of any flavor, absolute nor local, is what this would say for no extreme values. So that's a really good question. There's going to be one like this on Exam3. Not as tricky, but these are the things to watch out on for that kind of question.
You can have a local minimum, or you can't have a local minimum or maximum on the boundary, but you can have an absolute. minimum.
Absolutely, yeah. Let's actually add that in here. So boundary of the domain, let's say, let's maybe just type out a comment to go along with it. That might be a better way to go. The boundary of the domain of f is at x equals 0 is the first boundary point, and x equals 7. So that's just where the curve started and where it ends. Even though 7 is not in the domain, it's still a boundary point. We would write the domain like this. That is, the domain of f is 0, 7. But notice the way we had to write that out. The bracket right there includes the point 0. It just wasn't an absolute minimum nor maximum. And the parenthesis here excludes 7, which matches up with f of 7 being undefined. And now the really tricky part about all this is we get to say absolute, max, min values can occur on the boundary so long as f of 0, one boundary value, and f of 7 are defined. And notice we said can occur. It doesn't mean it will occur. It didn't happen on this one. But if we filled in this dot, like on version 2, it led to an absolute minimum. So absolute maxes, absolute minimums can occur on the boundary. It's just not a guarantee that they will occur. And this is the big caution. Local max, min values never occur on the boundary of any function. So no matter if it's completely open or closed off in both directions, we'll never have a local minimum nor maximum right at the end point of the boundary of the domain. It's always in the middle for local. Other questions so far, folks, about those tying together type comments? Okay, so these are the things that can happen with a graphing style question like this one. And take a look at the second version where we made the big change on this. But looks like we've kind of gone through this problem. So this is the change. Well, that's kind of hard to write on. Microsoft is really just not happy with this document for some reason. Kind of strange. This document was open locally, so you'd think a file generated off this computer itself would have ran better. So this is the change on this version. Well, which other questions would folks like to discuss relative to this third exam? Let me return to that section list.
The x squared part on the graph as well, how you explain the answer, like this is y equals x squared, I think. No, I think it's on the same chapter.
You're thinking maybe
On the I think it's on version 2.
also the lecture notes. Yeah, that's right. This one right here?
Yeah.
Gotcha.
So I would say, so to state the absolute maximum min values, so you would say, if the absolute maximum is at 2, you would say 4.
Yeah, that's right. This one's a little bit tricky because it wants specifically the values, whereas the problem on this one was just saying use a graph to state the absolute local minimum values. I guess it's saying it the same way, but here we were targeting mainly the f at 1, f at 2, and then mentioning the outputs. Here, you might say f at 2 is the maximum, and that'd be okay as well. We just couldn't say 2 is the maximum on this one. Should we give this one a try just to match it up with the last problem? Okay, let's throw this one in as well. So taking another look into this one, let me do something with the layout here. Okay, narrow margins just lets our graphics go a little bit bigger. I guess we can zoom in as well. So if we were going to find the maximum minimum values of the function on this one, here we would say f at 0 equals 0 is the absolute min, and that there is no absolute max. So the absolute minimum would be, let's just target the values here just to be more specific, is the 0 value on this one. But if you format your answer as f of 0 that way, you're saying the same thing. I would accept that as an answer. So these get kind of tricky. There's some differences when we go off to the next one, like you were mentioning. On this one over here, let's see what we've got. We have an absolute minimum just like before. So let's say f at 0 is the absolute min like before. And on the next one, we have f of 2 resulting in 4 because the function is x squared is the absolute maximum. But there's a couple different ways you could write this out for full credit. So you can either say f at 2 is the absolute max. I would accept that for full credit because it's true. Take the input of 2, and f of 2 is describing an output already, and that output is maximum, will be the maximum value. Or you can say 4 is the absolute max. So if you said it this way, that's great as well. I'd say in some sense, that's maybe the better answer because you're targeting the specific output, the function value as 4, which is that height right up here for the maximum. So far, equivalent answers. Or say, this is kind of redundant, but this is like the full description now. F of 2 equals 4 is the absolute max. That's what we were doing on the last problem. But this is where we could potentially lose points on the problem. Maybe we need a different color on that. Let's go with that one. But don't say 2 absolute max, since this is false. The absolute maximum value is not 2. It's just the input, which would take us to the absolute maximum, which is a 4 itself. So that's the dangerous one. We can't say 2 is the absolute maximum. It's really 4, or you could say f of 2, or just f of 2 equals 4 covers your bases in that kind of sense. Does that make sense to folks on kind of the challenge of describing the maxes and minimums? Okay, let's finalize the last one, just because it'd be weird not to. On this next one over here, we lose the absolute minimum because f at 0 is undefined, means no absolute min on that one. However, we do take an absolute maximum. We'll say f at 2 equals 4 is the absolute max. Then on this one, where we have fully an open set, there is boundary values. 0 and 2 are the boundary values of that domain, but they're not part of the domain of the function. This time we have f at 0 undefined. We have f at 2 undefined. So there is no maximum nor minimum on this problem. We can paraphrase by just simply saying no extreme values. A lot of the stuff that we've said on this so far are still pretty tricky. Anyone have any follow-up questions about any of these comments? Okay, well, let's keep on taking questions until we run out. Anyone in Zoom specifically have any questions that you have just burning off your chest that you'd like to ask about? Or anyone in class? Gotcha. Oh, we've got some chat activating. That's awesome. Abby says, can we go over example 2 in the 4.4 section that is on the second version? Yeah, absolutely. Thanks for the precise instructions on finding that one. So second version, I forget which versions I've opened up. Let me just open it up fresh. And we're going to example 2 in section 4.4. 4.4, what was that one? That sounds like optimization. So that's a good choice for sure. And example 4, that's a really good one to take a look into. This one's similar to the quiz problem, which means it's going to be a similar problem to the one you're going to see on the exam. I think on the exam, I gave a little bit more specific instructions. I said, use the first derivative test. You wouldn't lose points if you used the second derivative test. It would just be a much more painful problem to get through. So let's give this one a try. This is a great one to review for ahead of the exam. So we're looking into blood alcohol levels 10 minutes after consumption of hard liquor. It's given by that particular function down there. And we want to know at what time is blood alcohol at its highest? When does it reach its peak? In other words, we're looking for the absolute maximum. And the further instructions would say, use the first derivative test. So here's how this one will start out. Let me just get some extra space here. Microsoft has this weird thing where if there's not extra space on the document, I think that's what's messing up the digital ink on it. First thing we have to do is go to this function and just differentiate it right away. It's a complicated one to differentiate because of one factor, 26.9t, multiplying a second factor, e power negative 0.11t. This tells us right out of the gate, it's a product rule kind of problem. So b prime at t is going to be the derivative. Let me highlight this a little bit better. It'll be the derivative of the first factor, 26.9t. The derivative of that factor is just a 26.9. So we're going to the next step of the product rule. We've done this setup structure quite a lot that if you took this shorthand way of getting down there, that would be acceptable as well. But let me know how this feels. This isn't something we haven't done a lot in class. If this looks confusing on the derivative, I'm very happy to take a look into a second way of computing this. So I've differentiated the first factor. Product rule says you copy down the second factor. So e power negative 0.11t gets copied in, plus on the product rule. Now this time, for the second term, copy the first factor, 26.9t. Then differentiate the second factor. That's one where you probably want to be a little bit more careful. Let's do the derivative on the margin. E power negative 0.11t prime. Okay, we're taking its derivative. And our analysis on this one is that part is function 2, inner. And the base e exponential part is function 1, outer. So when we go to differentiate this, let me change the color here. When we go to differentiate this part, we follow directions and do the outer function derivative first. Derivative of that exponential is e to the power of something. We multiply by the derivative of the inner function. Here's that being put in. Now we have two placeholders. We just said multiply by the derivative of the inner function. So the inner function has to go here, negative 0.11t. But it goes in all of the placeholders. That's the pattern of the chain rule. It also emerges here, negative 0.11t. Then differentiating this will give us e power negative 0.11t. And the derivative over here is just a negative 0.11. Because of the way I wrote the base exponential first, I can't do this. That's saying we're subtracting when we meant to multiply. So I'll need to put in an extra parenthesis in first for that step there. So that's the derivative of this part. We carry it down, looking to what we did on the margin. Imagine scratch paper, perhaps. And we're carrying in e power negative 0.11t, negative 0.11. So in the color coding, anything that's in blue was differentiated. Anything that's in black was just strictly copied down. Any questions at all, folks, getting to this step? Okay, once we get to this stage, we're going to be equation solving. So the next thing we really want to do is begin to factor. We have a greatest common factor that's going to involve 26.9 e power negative 0.11t. Here's the 26.9 factor on the second term, and the factor e negative 0.11t clear over here. Doesn't matter where the factors are. If we have common factors across both terms, we can factor it out. And that's the best step to take at this stage. B prime at t is 26.9 e power negative 0.11t. So now that that's factored out, we're dividing it into this term. We get just a 1 plus that greatest common factor is divided over here. Anything not involving it is all that remains. So it's just going to be t. I keep forgetting that that's a multiplying. I'll just write it this way again, times negative 0.11, parenthesis required to show the multiplication. So that's our derivative in a more simplified form. Now, when we go over here and set b prime at t equal to 0, what that then implies is either this part is 0, but it's impossible because the exponential here is always positive for any input t whatsoever. The only way we get 0 is if this part goes to 0. So this means 1 minus 0.11t is 0 from that factor. And then now we can solve this really fast. 1 is equal to 0.11t positive. Divide 0.11 into 1. That's a weird operation. I'm not sure at all what that would be. Let's work it out this way. Comes out to about 9.09 minutes. It says round the critical number to 2 decimal places, so let's keep that a 9.09 minutes. So critical number, 9.09 minutes on this surge function that we have up here. At this point, we really have to show the steps of the first derivative test, so that's what we're going to do right next. This is half the battle, essentially. We had the derivative. It's not an easy one because the product rule and chain rule to run through. But once we get here, solving it was a little bit faster. And the next thing we do is we take this critical number. Let's make it feel important. Let's give it this color. Take that critical number, put it on the number line. This number line starts at 0 because the definition of t is minutes after consumption of a hard liquor. So we take the start of the domain when the experiment starts. Then this will be a t-axis for t minutes after consumption. We place the 9.09 right here for the critical number. And what we're analyzing in these intervals from here to here, and here way out to here, is a sign of b prime at t. I'll just call this, might as well call the whole thing b prime at t. So when we get to one critical number, it tells us b prime at t is going to take the same sign for every value in this domain and every value in this domain to the right of the critical number. So all we have to do is test one single point to get the total sign of the first derivative on this entire interval here and here. So that's the logic of what we're going to do next. We're going to take test values. What we're testing is a sign of derivative, and we need a number in this region. Any number is going to do the job. Let's maybe take 1. You could take 0 because 0 would be in domain on this. That'd be exactly when the experiment starts. But in certain problems, we saw one problem in section 4.4 where 0 is not in the domain. the one where we're building a box. If that ever happens, then this would be the next better value to take. But anything works. You could have taken a value 8, for example, a value 9, just not 9.09. Do B prime at 1 for the test number we selected, and we get 26.9 e to the power of negative 0.11. When we plug 1 right inside here, we just get 1 minus a 0.11. So that's going to be a 0.89. And this whole thing is positive. Even with a negative exponential here, we can check really quickly. E power negative 0.11 is a positive quantity as well. Doesn't matter how big this gets, it's always going to be positive. It's never actually 0 decimals, just has to eventually round if you give it a ridiculous exponent like this one. It's very close to 0, but not actually even 0. But because we got positive here, it tells us that B is increasing in this region. That means the blood alcohol concentration, this is the function that's modeling it, is going up. 0 minutes after consumption of the alcoholic beverage. That makes sense. Let me make sure it's hard liquor. Yeah, there's several different problems like this on the notes or in the other exam review materials. So blood alcohol is increasing. We need to now show blood alcohol is decreasing. And we know from intuition, yeah, after a certain point, it will decrease. But what we're checking is, 1, that it really decreases after 9.09, and 2, that the model made sense in the first point, that this model even has a maximum in the very first place. We don't necessarily know that until we check. So first derivative test resolves all those problems immediately. I'd say the next easiest value to test would be probably a 10, just for easier arithmetic. Do B prime at 10. Our whole goal is just to determine positive or negative. And this part doesn't even matter. It's always positive, but it's confusing if we don't put it down. So we wonder why we skipped it out. So I'll go 26.9 e power negative 1.1 after plugging a 10 in for t. But over here, if you plug a 10 in for t, rather over here, you get 1 minus 1.1. That's a negative 0.1, meaning there's only one negative sign in B prime of 10, forcing the whole thing negative. That's a moment of celebration because we wanted to show negative occurs the moment we go across that critical number. That now tells us B is decreasing. So blood alcohol concentration is now lowering. At this stage, our whole work is complete. We're ready to state the solution to that question there. At what time is blood alcohol level at its peak? We can say by the first derivative test, blood alcohol concentration peaks, or you could say is maximized, or the function has an absolute maximum at a certain time. Anything you convey that's along those lines would be just fine. I'll say blood alcohol concentration peaks at time. Just bring back the critical number. T equals 9.09 minutes. So it's a multi-stage kind of problem. You differentiate, and because it's an applied problem, the derivative is not always very nice. But I'm not going to make a big change on the derivative on the real exam 3. The big hints we've been giving out are this problem and the quiz problem and the exam 3 problem are all three going to be pretty similar, in particular the derivative as well. So study how this derivative goes and it'll be very helpful. The next stage is equation solving. So you have to get a factorization going on your derivative. The third stage is we have to show the number line analysis right here. It's a big part of the first derivative test in the first place. So it's a big part of the credit for this kind of problem. But this is what you're trying to show, either decreasing to increasing, or you're showing increasing to decreasing. You are expecting exactly one critical number. If all that lines up, just give a simple conclusion at the end. Well, thanks for asking about that one. I think that one is definitely a good one to include before finalizing our exam review. I'll turn it back over to the class. Any other questions about this one or other questions we should take a look into?
So,
Yeah.
you would do the second derivative and then set it equal to 0, and then if you got the definitive number, then you could be positive that that's the absolute max. Like you wouldn't need to do the first derivative test.
Unfortunately, even with the second derivative test, it's got some interesting steps. You're about right, but there is one weird thing about it. Let me see if I can pull up the notes on that one. So optimization, the thing about our second derivative test is it's been modified for this kind of situation. And the modification that's been made to it has one part that's just really hard to work through. So let's look through the steps of the second derivative test in view of the problem that we just worked on. If we want to run the second derivative test, it says, well, we have to have the second derivative continuous near a critical number. But that right there is where we get the critical number, f prime at c equals 0. Let's pause right there. That's kind of confusing too, because there are two kinds of second derivative test. Here's the other kind. In section 4.2, the other second derivative test is this one, a concavity test. So the concavity test and the second derivative test are two tests that are really easy to get mixed up on our mind. So with the concavity test, the steps on this one go like this. Step 1, compute f prime of x. Then step 2, you compute f double prime of x. Then step 3, you know what, I should probably go like this if we're going to describe the steps that way, just to make it super clear. We're describing steps of the concavity test. That would be a weird mix-up otherwise. So step 1, you compute the first derivative. Step 2, you need the second derivative. And step 3, solve f double prime of x equals 0. The reason we have to do that is if we're solving the region for where the second derivative is positive or negative, we need a critical number from this information. This is a critical number on f prime. And then it takes us to step 4. Let's say C is a solution. There could be multiple solutions on this one. It could be several values. You know what? Let's capture that here. C1, C2, suppose, let's add some words. There could be one solution here. There could be no solutions. Then it's only concave up on the entire real number line or concave down on the entire real number line. Or C1, C2 are critical numbers. I'll just say solutions briefly. If that's the case in step 4, we go like this. C1, C2. We analyze the sign of the second derivative and then apply the concavity test. Let's say, just for the sake of showing the concavity test, that when we test these regions down here, if this one comes out positive, we would say concave up. So shorthand for concave upward, written out that way. If it goes less than 0 here, we'd say concave down. If it goes less than 0 here, concave down as well. And there's oftentimes a step 5 on this as well. A step 5 would be, if you're doing a concavity test, oftentimes we want the inflection points as well. So step 5, state inflection points. Well, this one will have just one inflection point. An inflection point is when we change our sign of concavity, so it would occur here. There's no inflection point at C2 because with the example we made up and didn't quite finalize, there you go, with the example we made up, we just assigned the tricky situation, concave down, so we could discuss it. The only inflection point would be at C1, f at C1. F is the original function. So this is kind of tricky. We have the original function, a first derivative, we have a second derivative, so lots of information on the table. And this is how the concavity test would go. But now to return to that original question, how would the second derivative test work? It requires a critical number on f prime at C. Whereas down below, we want f critical number on the second derivative rather. So we would copy this information. We would still differentiate. We would still factor. We would still get the 9.09 minutes. So that's this stage. However, we skip all the way to this part because we're going for, hang on, let's go part B. We're going for an absolute maximum. We don't care about the local maximum at all in this one. So we have to show the second derivative after we calculate it is negative for all x. We don't even plug in the critical number on this one. You do it over here, but that's for local maxes, local minimums. What we need to do is differentiate this again and then show no matter what value t you put in there, the second derivative always negative, and that's for all x. That's the part right there that makes this tough, really tough. Sometimes it works out. Where it worked out really well was right here. When we differentiate this function once, we got 90x minus 75. And when we differentiate it again, we got something that's positive for all x in the domain. So we were just lucky on that function. However, this one, if we differentiate it a second time, it could be a challenge to show that inequality. I'll leave it up to the class though. Should we give it a try just as a challenge problem to see what could happen? Okay, let's attempt it. I'm not too sure if this test will even work on this one. It's not a guarantee that it's going to work. Let's see what we can do with it. So if we're going to attempt the second derivative test, let's pick up on that spot right there. We've already computed the derivative. Here it is. Let's just put it down here, far away. So we've already computed the derivative. Now we need to compute the second derivative. Notice it doesn't even mention the critical number, so that's why I didn't screenshot it and pull it in on this one. If we're going to compute next the double prime at t, we probably, well, we could differentiate this one, but it's a product rule. We could differentiate this one, which is slightly easier, but then another product rule right here. But hang on, let's bring in the original function to show how to do this really efficiently. Zooming in just for a larger screenshot. Okay, we've got all of our functions down the line. So b of t is 26.9 t e to the power negative 0.11 t. And when you look at that really, really closely, there is a shortcut here on the second derivative. I want to differentiate this line. I think this one's going to be a little easier. That's a new derivative we have to calculate. But 26.9 t e to the power negative 0.11 t, we have differentiated once already. It's the original function. That's kind of impressive in a certain sense, right? When we differentiate, or excuse me, yeah, when we differentiate b of t, that's the derivative, but b of t is part of that derivative as well. So if we go to take the second derivative, once we go to differentiate this part, we already have the answer. It's this whole thing. So we can just shove it into the result there as a massive speed up on the second derivative. So let's apply that method to see what we're going to get. We're differentiating b prime at t in either form, but this form looks easier. Differentiating here gives us the constant multiple rule first. 26.9. And we differentiate e power negative 0.11 t once already. So we probably want to cite that. This is what you would do in an exam setting, just to eyeball it. Okay, we got that as a derivative already. Just reuse that result. E point negative 11 t times point negative 1. So derivative right here gives, here's the negative 0.11 off to the left, e power negative 0.11 t plus Now, this is the weird part. I'm going to carry in this part first so I just don't forget, negative 0.11. Now, I'm differentiating the thing in the purple box, but the observation is you're just differentiating b of t, and differentiating b of t is that whole thing. So let's put it in. That times 26.9 e power 0.11t plus, actually, let me back off that step just a little bit. There might be an even easier way the more we look into this. So once we go to differentiate here, I've already copied the negative 0.11t down below. And then the derivative of the purple box is also this line. I think this is a slightly more simplified form to actually throw in. Let's use that form, already factored in a pretty nice looking way. So it's 26.9 e power negative 0.11t, another bracket, 1 plus t negative 0.11 goes in there. So that's the derivative of this portion, comes out into this stage. You know what, that's maybe too much arrows and everything on the emphasis. Let's pause right here for the moment. Any questions on getting down to that second derivative so far?
The front row, you can just do 26.9, and then you cancel off the negative 0.11, and then turn the keep it e negative 2.11 e times that by name. Oh, it would end up being the same thing.
Yeah, it looks like there's lots of ways to do this kind of result. Well, either way we get to it, our work is not done because we need to provide an argument that tells us this is always negative. This is where the second derivative test becomes a major, major challenge. I really don't have a clue how this one will go. Let's try it out and see what we can do with it. Probably what we should try is another factorization step. That always can resolve a lot of stuff. We have across all these factors, let's see, we can drop this bracket right here because this is just a straight multiplication through. That bracket was just to show this derivative being pulled in down below. Let's factor out all of that stuff because it appears here twice. So let's take 26.9, might as well multiply that at this step. Multiplied by negative 0.11 to get negative 2.959. Then e power negative 0.11t is going to leave behind from here just a 1. From here, it leaves behind the bracketed part. Plus, I'll drop the brackets, 1 minus 0.11t. So that's what we've got so far. See how this continues to develop. We have a negative sign in front, and that's pretty helpful for us. We're trying to show something's negative. Negative 2.959. The exponential part is always positive. That helps us. And on the inside, we have 2 minus 0.11t. Here's where it gets a little bit vague. Depending on the sign of, or the value of t, this could be positive or negative. It doesn't look like I have a good argument to show always positive on this one. Let me show you what could go wrong if we use a little bit more technology for this one. The graph of our second derivative is y equals negative 2.959 e power negative 0.11t. So that's the curve so far. And encouraging, right? Looks like it's always negative. Doesn't seem like it hits anything, or it doesn't hit the x-axis rather. But then we had this factor left over. One came from here, and 1 plus t power negative times negative 0.11 came from over here. So the next portion is 2 minus 0.11t. This actually intersects right at here. You plug in 18.18, it now converts positive. Well, once you go beyond that, we're positive beyond here. So it's not true that this is always negative. Let's look into the domain though. The domain of the function was at time 0 up to, well, it goes way beyond. Right where a critical number is right over here. So if we decide to end the experiment on a domain right around 15 minutes, second derivative test would have been active or applied here, but there's no end to our domain. So this test actually just doesn't work at all. It fails right here, despite the fact there is an absolute minimum right at 9.09 minutes. So that's the downside of the second derivative test. It's not a guaranteed test to work. Even if we were looking at it originally in section 4.2, there was a statement that this test can just outright fail on you. That's the part C right here. Whenever the derivative is 0, test has failed. So sadly, we have to say on this one, even though we did some good practice with the derivative, this is not always negative. And so the second derivative test does not apply. Not to say it's a bad test. We just have to be really mindful for this test. It's the finicky one. It can fit into certain problems if they look like, say, not that one. If they look like this one, they would do a good job. Or if you did a problem like this one, where we built up a cost function, your cost function takes a form like that, that's a dead giveaway. Second derivative test is great because we're not using any fancy techniques to differentiate this. We differentiate once, get a critical number, then we differentiate it twice. We saw that this is always positive because the x here is in a domain from 0 to infinity. This is a purely positive number now, and that meant for the second derivative test, we got this outcome. There is an absolute minimum for the conclusion on second derivative test. First derivative test would have been harder on this one, not excessively hard like this problem we were working on, but that's a good question to ask and think about. The reason the exam is going to say use the first derivative test is probably because it's the easier one to work. And we just discovered on our own just now, it's the only one that works on this one, unfortunately. But other questions are at the moment, folks, with either first derivative, second derivative test, or concavity test down below here. Okay, maybe one more reminder. When it comes down to doing the concavity test, this is a section 4.2 problem. And in section 4.2, the first derivative test for local minimums for maximum values is highly similar to concavity test. So the steps we just described from the concavity test work almost completely the same for this first derivative test. The only difference is you take out that step there and you solve first derivative equal to 0. And then everything else is exactly identical. It's so striking, we should just take a quick look at it to emphasize. Here's where we were doing that exact thing. The first derivative test is going to give us a local minimum, local maximum. We did it on this function where the second derivative test might have been easier, but we were just warming up to these methods. We found the first derivative, that's step 1. We set it to 0 and we solved it. That's the second step. And we found the critical numbers. That's the step where we place the critical numbers on the number line and begin our estimations. That's not the second derivative here this time. This time it's just the first derivative. The test values give us a sign on the first derivative, and positive just means function's increasing. On the last problem, positive, oh, hang on, not there. Positive meant concave up. Negative meant concave down. And we said here, negative first derivative means decreasing function. Then we just gave the domains where it was increasing, decreasing. In this problem, you would give the domains where it's concave up, concave down. Here, we're finding the local maximums, local minimums. That's where the sign of the first derivative changes. If it goes from increasing to decreasing, we have a local maximum. So that's what we said here, and likewise a local minimum. On the concavity test, if concavity changes signs, you have an inflection point. That's the similar concept to a local max or a local min, but concavity has to actually change signs. Just like over here, if this was decreasing to decreasing, we could not have said a local minimum at f of 2. There's no extreme value at f of 2. So as far as the actual exam is going to go, there's going to be 3.6, a problem on exponential growth or decay, randomly selected, some logarithm problems, some problems like we were just looking into, looking at local mins, maxes through a graph. We should be ready for a closed interval method or just a problem finding a critical number. 4.2, this is where it gets a little dicey. I can't ask all the questions in 4.2, the exam's too long. So I'm either going to ask a problem that looks like this, a concavity test question, or I'll ask a problem that looks like this, a local max, local min question. So just one or the other. Thankfully, the steps are similar, but we have to spot the differences on how to format our answers. Then finally, 4.4 is the problem that we've been hinting at for optimization. Take a look into the quiz problems or the problems that we looked into for guidance on getting through that one. But looks like we have about 14 minutes left. Any other concepts folks would like to take a look into so far?
So if there's only one critical point, then, and if it's a max or a minimum, that would be the absolute max or minimum.
Yeah.
If it's more than one, it would be only say it's a local.
That's true, yeah. If there was a couple critical points and we found information on a local values there, one of them could be an absolute maximum, but we'd have to do further analysis to really show that at that point. Other questions so far? Okay, well, this might be a good stopping point for us today then, just a little bit early. Switching gears back into section 5.3 after doing this much exam review is kind of jarring, I'd say. It might not be the best effort. So if you have any other questions when you're studying for this material, don't hesitate to ask. I'll be happy to help out. I'll be available on the weekend as well. I check my email on the mornings, Friday, Saturday, and Sunday. I'm actually working all day on Friday. But because we're going across into an exam week, I'm going to be looking in my email a little bit more on Sunday, or excuse me, Saturday, and quite a lot more on Sunday. So I'll be more available than usual. So if you have a lot of questions, just send them all out. I'll get to them individually, one by one, on a first come, first served basis. And I've never had a situation where I just ran out of time to ask questions. There's no way you could overload me on those. So don't hesitate to reach out while you're studying. I'll be happy to help out. Our exam is going to be on Tuesday, so that means, particularly for people who come in through the Zoom side, we won't have a class at all on Tuesday, but the 22nd, but we'll come back on the 24th. Well, have a great afternoon, folks. If you have any other questions, I'll be happy to help out. Otherwise, I'll see you all either next Tuesday or next week. Yeah, same time. It's normal class.